Up next, we're going to talk about nuclear energy. So it is a non-renewable energy, but it's a little different than the others. So it deserves its own presentation. It's the other non-renewable energy. Gotta love Homer Simpson. And our nuclear stacks right there that I'm sure everybody has seen before. And that smoke that's coming out is actually not smoke, right? It's steam. So keep that in mind as we go forward. So nuclear power is based on nuclear fission, and basically we use uranium-235. There are different isotopes of uranium. There's uranium-238 and uranium-235, and there's others too, but those are the big ones. And the 235 is the one that we use in nuclear fission. You can also use plutonium, but either way, they're stable, heavy isotopes. The isotope will actually absorb a neutron that is kind of pushed at it. And once that neutron comes in, it becomes unstable and splits apart. So it releases large amounts of energy. Also, it releases radioactive particles like alpha, beta, gamma rays. But that energy that's released is then used to heat water, to produce steam, and that steam turns a turbine, and the turbine generates electricity, just like all the other power sources, right, that we've talked about. And so this is a pretty self-perpetuating reaction, and it can be controlled mostly by having it cooled in water. And so that will be important later when we talk about meltdowns. But basically, this can be used in nuclear reactors or right to get nuclear energy or electricity, but it can also be used in nuclear weapons. It has a lot of energy when fission happens. So 1 kilogram of uranium releases more energy than burning 2 million kilograms of coal. Like the amount of energy you get from a tiny bit is a lot. And there is natural radioactive decay on Earth, which we'll talk about a little bit, but fission is not natural, right? This is man-made, we're doing it. So a little more about uranium-235. Not a lot of uranium is 235. It's actually mostly uranium-238. So only like 0.7% of the world's uranium is the kind that we need. It is non-renewable because there is a finite amount of uranium in the earth, just like oil, right? So it is non-renewable. And so uranium, the only uranium isotope that can sustain this fission chain reaction is this 235, and that's why it's so important. So we have to mine for uranium ore, and then we mill it to actually get the uranium out of it and refine it into a higher percentage of uranium. And then we take that and we enrich it using chemical methods to get the amount of 235 to increase. So it goes maybe from like 0.1 or 1% 235, and in nuclear energy we need it to get up to at least 3.5%. Once we do that, we put it into these little pellets and put them into rods, and that assembly is what we use in nuclear power. We put it into a reactor. And so a little bit about radioactivity. Like I said before, the fission is creating heat, which we use for that electricity generation, and it is also releasing radioactive particles. Like I said, alpha, beta, gamma rays. The reason why we worry about this is because radioactive particles can harm tissue, like by direct contact. and or also just damage DNA. So when DNA is damaged, it actually causes cancer. It's basically a mutation caused by this radiation. And so we contain this radioactivity in these confinement structures, and when those confinement structures are compromised, that is when things go poorly. It's really important when we talk about radioactive material, we also talk about half-life. And so any radioactive isotope decays, meaning that if it's radioactive, it's going to break down and emit radiation. And the time it takes for half of it to decay is called a half-life. Now, naturally, like there's carbon-14, which is a type of radioactive carbon, and that breaks down, and we actually use that material to do carbon dating. I'm sure you've heard of it before. And it's not, that's not, that's natural, and it's pretty, it's not dangerous. But anyway, it's important to kind of understand this concept of a half-life. So I'm going to try and draw on the slide for you here. So let's say if I have the percent of substance remaining, if it's breaking down by half, right, it's 50%. That would give me 1 half-life, and on it goes. So like that 50% is broken down by half, right, would be 25%, and right, each of those materials is going to get broken down by half, by half, by half. So like 100, 50, 25, 12.5, and on it goes forever in perpetuity, right? And in general, when we talk about these heavy isotopes and looking at radioactivity, usually we say that after about 10 half-lives, it tends to be safe. So let's look at uranium-235 and think about how long it might take for it to be safe. So if I were to look at the decay graph of uranium-235, take a look. How long is a half-life of uranium-235? So my percent remaining is 50% because it's half. And here I am on my graph there. And so what is that? If you said about 700 million years, you'd be right. Okay, 700 million years. And so how many years would 10 half-lives be in order for uranium-235 to become safe? Well, 700 times 10 is 7,000. So we're looking at 7 billion years for uranium-235 to be deemed safe in terms of radioactivity. The Earth is not that old, so yeah, that's a long time. But let's right, that's when we talk about radioactive material, we're not really talking about uranium-235. The products of fission have shorter half-lives, but still not very short. So, right, our nuclear waste, so the spent fuel rods, when there isn't enough radioactive material to be used in that power generation, they're still emitting radioactivity. So there are these fission products like strontium, cesium. They are, right, they have a shorter half-life than uranium-235, but basically they're not considered safe until after about 24,000 years. And that's, again, right, about 10 of their half-lives. So still a really long time, much longer than a human lifetime. And we're going through these rods about every 3 to 6 years. So we need a place to store them so that radioactivity isn't just, getting into our groundwater, getting into our surface water, just emitting out into the air and precipitating back down on us. And so what we do is we use these storage containers in their cement and I want to say steel, and we just store them in like little rows like this. Not little rows, they're big. And so if you could imagine the amount of nuclear power that's generated and how often we need to change out the rods, it takes up a lot of space. And so we need to store them for long periods of time. So, beyond uranium not being renewable, is it sustainable? Like, how are we going to keep storing this? Not only that, it needs to be like far away from people. So, we're just like using land to store this waste product. And it is, there's no real good solution for it. 24,000 years, it's a really long time. But even like, despite the nuclear waste, it's actually what they call it is high level radioactive waste because it's still pretty radioactive. We do consider nuclear energy a clean energy source because it doesn't release any air pollutants to generate electricity. So as it's going through that nuclear fission, there is zero carbon emissions coming out of there. However, the process to actually get to that point is not zero carbon, right? Mining it, you get all of the same problems that you have mining anything else. Enriching it using that chemical process, and then actually physically building the plant. Of course, we're going to use materials and machines. So carbon emissions are zero, but only while it's operating. But what it does create is thermal pollution, and you're like, no big deal, who cares? It's just hot water, right? But, that has serious ecological effects. So the water that's used to cool the process, so not the water that's actually exposed to the radioactive material, but the water that's used to cool the reaction is discharged in nearby water. And so this water can be anywhere from 30 to 40 degrees centigrade. So you're looking at 86 to 104 degree Fahrenheit. That's significantly warmer than the surrounding water bodies. I'll tell you about Millstone in a little bit, but basically Millstone dumps into Long Island Sound, and that's Connecticut's nuclear power plant. And I don't know about you, but I don't think the Long Island Sound is that warm, ever. And so, right, these warmer temperatures affect water quality. We haven't talked about it yet, but dissolved oxygen is temperature dependent. And so with increased water temperatures, the amount of oxygen dissolved in it is lower. pH will increase with warmer temperatures. And then it also increases decomposition. And so, again, we haven't talked about this yet, but when you have an increase in decomposition, the bacteria that are decomposing the organic matter are actually using oxygen. And so you end up with hypoxic water or low oxygen environments. And again, we'll talk about that more when we get into water pollution. And then just the decrease in biodiversity. So either organisms are moving away, or if they're vulnerable or they're not able to move, they will die. So, remember, move, adapt, or die. This is happening too fast for them to adapt. So move or die. Like I said, Millstone is in Waterford, Connecticut. It actually has 2 functional reactors. There are 3 on site. One was decommissioned, I want to say in the 90s. Anyway, there are these fallout plans basically where there's like a 10, I think like the initial plume is like 10 miles or something, but then the ingestion pathway zone, meaning like once that radioactive material precipitates down and you can then ingest it in like from water and your food sources and stuff, is about 50 miles away. And Hartford is within that ingestion pathway. So when we talk about these next nuclear accidents, keep in mind that, how many people would need to be evacuated if something were to happen at Millstone. So the first one I want to talk about is in 3 Mile Island. This happened in 1979. It's in Pennsylvania. It's the largest U.S. Nuclear accident. Now, there was a partial meltdown of uranium, meaning the uranium actually starts melting and the reaction is a little uncontrolled, but they were able to get it under control. So there was no explosion or long-term radiation exposure. What actually ended up happening was a malfunction of this pump that didn't allow water into the reactor. So, right, there's this like pump down here, and then it puts water into the reactor to cool it off there. And what happened was that the water wasn't filling the tank. And so it wasn't cooling the reaction, and the uranium started melting. But they were able to bring it back. So that's good. No long-term radiation exposure and no explosion. As opposed to Chernobyl, which I'm sure everyone has heard of. This was in, the USSR, the Ukraine, in 1986, and it is the largest nuclear disaster in history. Basically, it was a safety test gone wrong. So they simulated a power outage, and they they miscalculated how much power they could actually generate from the turbines from before this power shut off. And so when the power shut off, the backup power that was there actually wasn't able to maintain it. And so when they tried to shut the reactor down, it failed. And so the nuclear reactions continued when it should have been shut off, and it caused a total meltdown. So that means that all of the uranium in the reactors actually melted down. And so it was so hot that this superheated water caused an explosion of steam because it was so hot. And then there was also a fire in the reactor core. So simultaneously, those things happen, and it ended up putting this radioactive contamination into the air. And you can see how far it actually went in that lower picture there. And so basically, amazingly, only 2 staff died in the explosion immediately, but more died in the days to come. And there was this exclusion zone of 6 miles, which they then extended out to about 20 miles, and they evacuated over 100,000 people. Just looking at the fallout afterwards and looking at models and health data, from the 3 Soviet states, you have about 4,000 people estimated had died from Chernobyl. So this is really just from radioactive material, and mostly thyroid cancer is the big one that it caused. And then just all across Europe, about 16,000 fatalities. So, it had a pretty massive effect on just humans, and then add in the environmental consequences of the area around it. Just the tissue damage of you can see this red forest up there. The tissue damage of the trees was extensive. And so basically there's just all radioactive material, and the organisms that lived around there died, from radioactive, from exposure to radioactivity. And so in order to like reduce the spread of radioactive contamination, they built a sarcophagus or like a structure over the reactors. And now it's a tourist destination, so you can actually go back there now, but only with a guide in that exclusion zone, and you're not supposed to touch anything. So they like measure the amount of radioactivity. What's actually really interesting about Chernobyl is that exclusion zone is basically a wildlife rescue now because they don't really touch it. And so a real interesting case study of secondary succession. So the most recent one was in Fukushima, Japan. There was actually a tsunami that that caused this meltdown. So there was a 9.0 earthquake, and that caused a almost 50-foot high tsunami that struck the power plant. And so the reactors actually flooded, and the emergency generators failed, and so the cooling pumps that are supposed to cool the reactors actually didn't bring that cooling water in there, and again it had a partial meltdown. So not only did we have a partial meltdown, but then there was a buildup of hydrogen gas, and there was explosion. So 3 of the reactors actually exploded. They evacuated the area. Really interesting about this, though, is the radioactive contamination went into the Pacific Ocean. So with the retreat of those tsunami waters, it actually retreated back into the Pacific Ocean. You can see in that lower picture there from NOAA, the radioactive material was basically in the ocean and went towards the west coast of North and South America. Since then, there's been upgrades to the power plant. They've added in flood control and seismic activity monitoring. So, they've learned from their mistakes. And so, these are things that can happen with nuclear power, but if things are run well and planned, meltdown is unlikely. No carbon emissions. And on the flip side, getting to the power plant and the nuclear waste and the thermal pollution, are definitely disadvantages as well. So is this a solution to our energy dependence? You decide for yourself.